perhaps for the last time. Is anyone willing to help us with the presentation today? Okay. If there is no one, if you've already presented and you are willing to help us again, feel free to pick up. Is there anyone who has presented and is willing to present again? Okay, thank you, Tanya. So today's discussion is going to cover the last part of the RBC, which is the math aspect of it. And I sent the file to you guys, I believe, last week. So this is what we are going to go through in terms of the understanding of. If you just joined, please mute your mic. If you just joined in, please mute your mic. So this is going to be the file that I sent on Canvas. So I'm going to take you guys through the math, okay? If anyone has any question from last week, please let me know before we move on. Any questions from last week? Okay. If there are no questions, then we can just start right away and have a look at how to solve the household problem. Then we'll move on to the firm's problem, which is technically the same as the ones that we saw in the two-cycle model. This is a bit complicated in terms of the notation and in terms of the time span that an individual is expected to live. So please keep an eye on it as to how we will go with the Lagrangian. So make sure you stop me if something is not clear, because it's a bit unusual as to how we solve the Lagrangian here. So please keep an eye on it and let me know if you have issues with it. So with this model, it's the same RBC model, individual live for a given amount of period. For now, we assume that he lives for an infinite amount of periods. So that's why we have the t starting from 0 till perhaps infinity. So this is very important for us to note. In a situation where we have a two-cycle model, where individual lives at time t0 and t1, then this becomes 0, this becomes 1, in which case this equation just becomes a usual equation that we know already, which is beta to the power 0, u as of time 0. You put in its utility here, beta to the power 1, you put in its utility here, and off it goes. So this becomes a situation where we start summing for only two periods, for period 0 and for period 1, which is the same as the usual two-period model that we saw. So we are moving away from just simplistic two-period to an infinite amount of periods. So we now have infinity. So this will be the first thing I would like you guys to pay attention on. Is there anyone with a question in there? So instead of two-period, we now have an infinite amount of period for the individual. Having said that, the next line of action is to understand this guy. And I believe, given what we did earlier in terms of the utility function, so remember, we said an individual has 24 hours to make his or her own decision as to whether he would like to work, which is N, or whether he would like to have leisure, which is L. And we normalize this 24 hours to 1. And we normalize these guys in fractions. So we have n, and then we have small l, which is equal to 1. So whenever you see 1 minus n, it basically tells us the leisure that the person has. So instead of writing c and leisure here, I can equally write c and 1 minus n, which is the same as leisure. So there shouldn't be any confusion in there, given the further explanation. Is that okay with everyone? Tanya, is there anyone with question in there?
No questions.
So we now have the leisure, we now have the consumption, we now have the time frame. The next line of action is to understand the budget constraint of the individual. So I'd like to take you guys back to what we saw earlier in terms of the two-period model and how that falls in line with this guy here. So remember, in the two-period model, we said an individual has a budget constraint where he has his C, which is his consumption, plus he saves part of it, equals his income. This was the simplistic budget constraint that we saw in the two-period model. It's the same as what we might see here. So his income, instead of having his income coming from only work, because he works an amount of hours, he gets paid W, which is the same as what we see here. We also assume that he gets an additional income from renting his capital. So for instance, you have a laptop, you give your laptop out for someone to go and use it, the person will pay you rent. So this is the additional rent that he gets from the capital that he owns. We also assume that he has an investment elsewhere, maybe in the financial market, be it a bond or maybe any form of security that he might have. The bond that he has pays him interest. So this is the interest that he gets. So in addition to capital and working to get income, he now has an additional income that comes from the financial market. And lastly, as we assumed from the initial setting, he gets profits from owning a firm. So we said household do own the firms. So all the profit that were realized from the firm's decision or from the firm's outcome goes to the household. So directly it counts to his budget constraint. So this becomes the new setup. The only addition we have here is the fact that we now have rental income and we now have investment income from the bond market or whatever market you might want to pick it from.
You've got a question?
Sure, feel free.
Someone asked, what happens to taxes?
Yeah, you can equally put in taxes. In the second example that I'll be looking at, we will look at taxes. Again, if you might want to put in taxes, you might assume it to be a lump sum tax minus big T. It doesn't really cause any trouble. Or you might want to call it a unit tax, which might be very intuitive. So it depends on which tax you are interested in finding. If it is a unit tax, then it becomes a bit complicated. You might want to pay attention to that. But if it's a lump sum tax, then it just goes away. It's not that interesting in this setting. Is that okay? So if you happen to find yourself here, just type your full name and type present before we continue. And let me know whether you guys have further questions. So this becomes his budget constraint in terms of the income side. We now have to go to his investment side. Now for the savings, this is the same as the consumption that we saw earlier. His savings, as we pointed out, he might be interested in saving in either capital or saving in the financial market. So it might be a situation where the excess amount that he has, he will save portion of it onto the bond market, which will fetch him an amount of interest for the next period, or he would just invest an aspect of it in the capital market. So this is just by way of his new budget constraint. So let me be sure if you guys have any questions, please stop me if something is not clear. So I hope this budget constraint should be fine for now. The next line here happens to do with what we saw earlier in terms of the law of motion of capital as we saw in the earlier sections, be it in the solo growth model or in the two-period model. So the capital for tomorrow is the same as the amount of capital that you have for today. But remember, for every capital, there comes something that we call depreciation. So when this depreciation sets in, the amount of capital that you have today goes down. But because you have an investment that you always make in the capital market, the amount of your capital also goes up, given the fact that you are investing in capital, which is your X of T. So X of T is the same as this guy plus minus this guy. And this is a depreciation. So nothing new. Okay, so that's the law of motion of capital. And other further technicalities, we assume that the capital should be greater than 0 and what's not. So that wouldn't be significant in this setting. But we need to make the assumption that there's no negative level of capital.
We've got someone asking what X is again.
X is your investment. So X is the same as the I of T that we saw earlier. So remember, we saw an I of T in the solo growth model, in the 2-period model. I is the amount of capital, investment in capital. Remember, do you remember this equation, the law of motion of capital in the solo model? Yeah, so that's it, yeah. So X is the same as your I, which is your investment, and it goes into the capital market. Further questions? So is it safe for me to change it to X of T again, just so you guys are okay with the notation in the file that I sent? Okay. So let me quickly change this guy back to small x of t so that we have the same notation as what we have in the file. So this is just the setup.
We've got someone asking if you could explain the first condition once again.
Well, which condition? Sorry, is it a budget constraint or this guy? Which one?
I think budget constraint.
The budget constraint. Yeah, so the budget constraint is basically your consumption. So this is your income, the total amount of income you have for a period. Out of this total amount of income that you have, part of it goes to consumption, part of it goes to investment in the financial market, and part of it goes to investment in the capital market. So instead of we having a very simplistic view of your budget constraint, wherein we said this is your income, you save part of it and you consume part of it, we are now saying that we want to be more specific. So your income comes from work, plus it also comes from capital investment that you have. It also comes from your financial investment that you have. It also comes from the firms that you own in terms of the profit. So this is your income. Instead of this simplistic view of income, we now have a more comprehensive view of income. In terms of the savings, this is a bit naive as well. So we might want to say you save part of it in capital, invest in capital, and part of it is you invest in financial markets. And the C is just the same as C in terms of the consumption. Okay, good. So let's quickly move on to the Lagrangian for this.
We've got somebody asking, does B have to be positive?
Does B, it can be positive or negative. In the situation where you have it to be positive, it means you are making an investment in the financial market. In the situation where it's negative, you are rather borrowing, right? Yeah. So you can borrow from the market or you can save on the market. So when B is positive, you are saving. When it's negative, you are borrowing. Yeah, that's a good question as well. So let's quickly go back to the setup and let's work the Lagrangian. So I'm going to bring this guy here and quickly change this guy into a Lagrangian equation. So back to what Ella asked, I'm going to change the x of t into this new law of motion of capital and replace it here. So let's have a look at it. X of t can be said to be kt plus 1 minus 1 minus delta kt. If that's the case, if this is x of t and x of t is this, then I can go back and replace x of t with this guy. So the budget constraint no more becomes ct plus bt plus x, but rather c plus b plus this guy here. So everything will be in terms of capital. So you make a decision as to how much you like to work, how much you like to consume, and how much you like to invest based on what we have here. So your Lagrangian is going to look like this. We have L, then we have your utility here, which is expectation, summation to infinity, B of t, U, C of t, 1 minus N of t. This is your summation. Plus or minus, whichever way you might want to go with it, lambda. And this is where I would like to point out. Here, instead of having a constant lambda, which is just a lambda, here we have a lambda as a function of t, because you have an infinite amount of period that you do leave. So this constraint, for every period, you face this budget constraint. So there's a need for us to have a subscript of your lambda. This guy here, we have your C of t plus bt plus 1, just like what we saw, plus your x of t. But remember, your x of t just turned into kt plus 1 minus 1 minus delta k of t. This became your x of t, just like what I did earlier. Minus w t n t minus RT KT minus big RT BT minus pi of t. Was that all? Was that all the income that we saw? Your income came from wage, capital, financial market, and profit. Well, is there any additional one that I might have skipped from the budget constraint that we saw? If there is, please let me know. All good?
Yeah, I think we're good.
Okay, good. So this is your budget constraint. And just like what we saw in the earlier section, we differentiate this guy here with respect to C of t. So I go through this guy, find where I can see C of t. So there is a C of t here. So this is going to be B, T, U, C. So I'm differentiating this function here with respect to C. So that's why I have it. Let me make things much easier. D, U, D, C, T. Plus, there's a lambda t here, and there is ct here, but it's only ct. So it's just this equals 0. So this will be the first derivative that we might find when we differentiate with respect to c of t. Is that okay with everyone?
Well, we've got a question. Alex is asking, do you ignore the expectation E?
Yeah, you might feel free to ignore the expectation at this point in time because they are of the same time period, right? So if you are in today's time period, it is okay for you to say that I know what's going on. So I don't necessarily have to form any expectation. But if you are looking far into the future, maybe t plus 1, then you might want to form an expectation, right? So this is, yeah, is equally valid, unless of course you define the times subscripts differently. I might want to put the expectation of E here. It doesn't really cause any much of a difference if they are of the same time period. Question?
Yes, we've got a question saying, can we convert the utility function into natural logs to solve the first part?
Yeah, for now, I've given you guys a functional form of the utility, right? So I'm not giving you guys a functional form of the utility, and I'll be doing that after I'm done with the theoretical step in solving it. So for now, there's no utility function. This is the general way of solving it. after introducing you guys to the general way of solving it, then I'll give you guys a utility function and you guys will struggle with that, right? So that'll be something you guys will work with. Is that okay? Is that okay?
Yeah, I think it's good.
Okay. So for now, there's no utility function. That's why this derivative, we've not been able to give any functional form for now. So we just leave it as this. So back to Alex's question, you might want to put expectation here, is fine. You might want to leave it, it's just okay. But if it is t plus 1, then you need to be a bit more careful. Then we do the same thing with respect to n. N of t or n. Again here, you have to be very careful. Just like what Lane asked, because there's no functional form, you have to go the general way. So just the expectation here. There's bt in front of the n, so I keep the n. I differentiate the function with respect to n, and I put the solution over there. There's ct here. There's 1 minus n of t here. Then I do the same thing again. I go through the other side of it, see where I'll find n. There is lambda t here, which is for sure. There is no n, there is no n, there is no n, there is no n. There is an n here. But remember, it comes with a w. So this becomes minus wt with the n going away, and this guy goes to 0. Is that okay? If you have questions, let me know. Is that anyone with any question?
No questions.
Good. Then remember, you are also making a decision as to how much to save, and you either save in terms of bond or you save in terms of the capital market. And this is where it's a bit complicated. So keep an eye on how I'm going to do this. So let's imagine a situation where you are making a decision as to how much to buy in terms of your capital for tomorrow. So this is KT plus 1. Right? For capital for today, there's nothing interesting about it. Just like what John pointed out the last time, if you are in today and there's a shock, you can't do anything about your today's capital. What you can do is about your tomorrow's capital. So that's why capital, you have to differentiate with respect to KT plus 1. Differentiating the capital with respect to KT is not intuitive. It doesn't make sense, right? So you make a decision as to how much to save for tomorrow in terms of your capital investment. I come here, I check, there is no capital here. So I go, no problem. There's a lambda t here. There's a capital level here. So I have a lambda t kt plus 1. But it goes away, right? So just multiply it with 1. Because it just goes away. This is the KT. You differentiate with respect to KT, it goes away, so I'm just left with lambda. There is no KT plus 1 here, there is no KT plus 1 here, there is no KT plus 1 here, there is no KT plus 1 here. I'm done with the first part. Right? I'm done with the first part. And this is where you guys might find a bit challenging, so please keep an eye on it. Remember this guy here happens to be your constraint for every period in time. Let's take the situation where you are in period T. Whenever you are in period T, you have lambda T. When you find yourself in period T plus 1, what will be your constraint? Your constraint therefore becomes lambda T plus 1. CT becomes CT plus 1. BT becomes BT plus 2. KT becomes KT plus 2. Now this guy here, this is where I would like you guys to pay attention. This now becomes minus 1 minus KT plus 1. Right? So when I move one period ahead, my lambda becomes lambda plus T, my CT becomes CT plus 1, and my KT becomes KT plus 1.
We've got some questions.
Yeah, feel free.
So someone asked, did you mention the sign in front of lambda is irrelevant because they're confused about the sign of lambda times W in the second equation?
the reason why I have, so lambda here, when you have a positive sign here, keep it as positive. When you have it negative, keep it as negative. It doesn't really cause any trouble, just like what we saw in the two-period model for the Lagrangian. It doesn't really, change anything. If you have it positive, just keep it positive. If you choose a negative value for it, keep it as negative. But what is most important is when you differentiate any of these guys, make sure you keep the sign that counts with them. So when I differentiated with respect to CT was positive. That's why this guy remained positive. When I differentiated with respect to NCWT had a minus in front of it. That's why I kept the minus here. Was that the question?
He's saying in the notes, the second equation is different in terms of lambda times W.
We will arrive at the same conclusion. Yeah, we will arrive at the same conclusion. What you guys are trying to point out here is, if you come here, okay? I see what you guys are trying to draw. When you come here and you use a functional form, remember this guy is 1 minus n. So when you differentiate this guy, right, with respect to 1 minus n, there will be a minus sign here. And with this minus sign and this minus sign, it goes away. It becomes positive. Is that okay? The negative sign, why you don't see it here is, this guy is minus. When you differentiate this guy with respect to n of t, I differentiate this entire function, I differentiate what's inside as well. So this is this guy multiplied by minus 1, right? So this is minus, it goes away. So that's what you see in the note. But because I've not introduced a functional form, that's why you don't see it. But it's just the same thing. Is that okay?
Okay, so that's good. And then Jean-Luc had a question. So the E is always maintained. So is it being multiplied by the whole function? And is that why we keep it? Because it's multiplied by WT times NT. So it comes out negative, or negative WT times NT.
What was that? Sorry.
Oh, okay, sorry. Just the first part. So the E is always maintained. Is it being multiplied by the whole function? And is that why we keep it?
Yeah, because there's expectation. Yeah. So just coming back to your questions, the reason why we don't see this guy to be negative, imagine I give you, so the reason why you guys see this guy to be minus and it's inconsistent with the notes is when you do a proper differentiation of this, which I intend to do with a functional form, the minus sign is here. So with this minus sign, it comes somewhere here. And with a minus and minus, everything turns to positive. So I don't know which one you guys would like to go. So for us to be consistent, let's keep with the notes. Minus, minus, everything goes away. I end up with a positive sign. No issue. Is that okay? Now let's go back to, so let's go back to the Lagrangian. So with this constraint, when I move it 1 period ahead, this is plus 1, this is plus 1, and this is KT plus 1. So I end up with plus lambda t plus 1. This is KT plus 1 into brackets minus 1 minus lambda, and I'm done. And this is where you guys can, stop, ask questions. Let's see how we can solve it. And there is also KT plus 1 here with regards to the return on investment. So this is RT plus 1, KT plus 1. So at the same time, it's going to be minus RT plus 1 equals 0. Questions? If you move the lambda to the third period, everything goes away. There is no plus t again for the capital. Questions?
No questions.
Okay. Let's do the same thing for the investment in bond. So we have the L, the BT plus 1. I start again. I look for where I might find BT plus 1. There's a BT plus 1 here. So I start with just lambda t. There is no BT plus 1 anywhere again. So I stop. Because it's plus 1, I will try as much as possible to move the time period one step ahead and see whether there is an additional plus 1 showing up. When I move this guy one period ahead, there is going to be a certain minus RT plus 1 with a certain BT plus 1. So I need to consider that as well. So I end up with plus lambda t plus 1 minus RT plus 1 equals 0. So these are the three most important equations that we have, or four most important equations that we have, and we can now merge them and make decisions out of them. So I'm going to stop here. Feel free to ask questions if you have any. And we can use a functional form as well. Is it safe for me to clean it? If it's not safe, let me know. I want to clean this guy.
Oh, we've got a question. Do we bother differentiating with respect to BT as opposed to BT plus 1?
But remember, it's the same idea, right? So BT and KT has the same intuition, just like what you pointed out the last time. BT is a savings that has been determined within this time period. So you don't make any decision based on BT. You make decision as to BT plus 1. How much do I see for the coming year? Because whatever has happened has happened. Just for the same case for the capital, we don't differentiate with respect to KT because the capital level has been determined for today. We only make decision for KT plus 1 because that determines our savings for the next period. John, was that your question?
So he's saying, so we're differentiating the choices, not the constant / exogenous stuff.
Exactly. Yeah. Yeah. These are your choices that you make for the, these are the choices that we make. If you have further questions, please let me know. So I'm going to join these equations, just like what you guys see in the notes. And given what the questions have been receiving, I have an indication that you guys have read the notes. So I hope it's much clearer as the note has it. So we are just going to play around with the equations that we have here, starting from equation 1. If you use equation 1, I call this guy equation 1. I call this guy equation 2. I call this guy equation 3. And this is equation 4. If I use equation 1 and equation 2, the same idea that we saw earlier. Equation 1 said beta t differential of u with respect to c equals minus lambda. And equation 2 says that technically the same thing. bt du of c dn equals minus lambda t. So I just come here and I divide it with w because there's a w here. So I don't want to cause any confusion. So as we saw in the first Lagrangian, lambda is the same as lambda. So minus lambda is the same as minus lambda. So these two equations will end up being du of c beta t is the same as beta t du of c dn multiplied by W, and this guy will cancel this guy. So this is what we call your intratemporal decision making. Intratemporal. Intra. You are making a decision as to how much to consume and how much to work based on this guy. So whenever we ask for the intratemporal decision making between consumption and amount of hours of work, you can use these two equations and fetch it out. Yeah, sorry.
We've got a question. What does the dNW represent on the bottom there?
Yeah, it's just 1 over W because this guy came with W, right? This guy, it came with W here. So I had to move the W down here so that I can isolate the lambda and lambda. Is that okay, John? The W is the wage. So before you make a decision as to how much to consume in terms of your consumption and how much to work in terms of your leisure and amount of work, this is what we use to make the decision. So intra means that you are making the decision within the same time period. So this is very important. Whenever you hear intra, it means within the same time period. You are not making a decision between today and tomorrow. You are making a decision today between two variables. So it's intra. If you are making a decision between today and tomorrow, then we call it intertemporal. So any decision between two periods, we call it intertemporal. And we'll see an intertemporal decision making right away. So this is between two periods. And this is within the same period. If you have questions, please let me know, okay? So having combined equation 1 and equation 2 to get the intratemporal decision making between consumption and work, why not use equation 3 and equation 1 to get your intertemporal decision making? So I'm going to use equation 1 and equation 3 to get your intertemporal decision making. Let me know if you have questions, okay? So remember, this is what I have. Data T du dc T equals minus lambda T, right? The same idea that we saw earlier. I can move this guy one step ahead. With this same equation, I can move it one step ahead by adding 1 to the subscript. So if that's the case, this equation, duc dct, this therefore becomes plus 1, and this becomes plus 1. I've not done anything new to it, okay? And if that's the case, I now have an equation that involves lambda t and lambda t plus 1. So using this equation, lambda t is basically this guy. Put minus here, put minus here. This is lambda t, bt, u prime, dct. That's this guy, okay? Plus lambda t plus 1. I know the same intuition holds, so bt plus 1, duc, dct plus 1. This is this guy here. Now I know it comes with some additional stuff. So why not put those stuffs over there? And these are these guys here from equation 3. So I'm going to put them here. Minus 1 minus rho minus r t plus 1 equals 0. So I'm done. I've been able to get your decision making between your consumption for today and your consumption for tomorrow just by combining equation 1 and equation 3 and moving equation 1 one step ahead. So this here is what we call the Euler equation. And it helps you find your intertemporal decision-making process. So I'm going to stop here. Ask questions if you have any. Tanya, is there anyone with any question in there?
No questions right now.
Okay. So before we go ahead, please type your full name and type present, and let's go ahead. Okay, I'll wait for some time. If you have questions, please ask. If not, then we can go ahead and finish the last two equations here. The last two equations here. Okay.
Yeah. Got a question. Oh.
Yeah.
Is that a negative beta in front of each equation at the top?
I think so. Yeah, because when I move the lambda here, it's supposed to be negative, right? So when I draw this guy, then the lambda needs to be negative. But I have to move the negative to this side. It doesn't change the dynamics. If you are to keep the lambda to be negative from the beginning, everything is just the same. Questions?
No more questions.
Now let's quickly combine equation 4 and equation 3. Okay, equation 4 and equation. You can also combine equation 2 and equation 3 and make the same intertemporal decision making in terms of amount of hours of work between today and tomorrow. So that you should be able to capture. Equation 2 and equation 3, you can use it to capture your decision as to how much you would like to work for today and tomorrow, which is the same as your Euler. Equation 3 and equation 4, so rather unfortunate that I canceled them, but let me use what I have here. I think equation 3 gave us something like minus lambda t plus lambda t plus 1 minus this guy here plus RT plus 1 equals 0, something like this. And equation 4 gave us minus lambda t plus lambda RT plus 1 equals 0. Now, what do we see here? This I find to be very intuitive, right? So remember, this is what we had when we differentiated it with respect to KT plus 1, which is your capital. And this is what we had when we differentiated it with respect to the bond market. This cancels this. This also goes with this. So you end up with RT plus 1, which is your return from the financial market, to be the same as the return from the capital market. It makes sense. So if you're an individual and the return from your capital market is above the return from your bond market, will there be any bond market? Will people go ahead and invest in bond if they expect to have higher return in capital? Right? Questions? This is your capital, this is your bond. The intuition from equation 3 and 4 is that the return from capital should be the same as the return from the bond. In a situation where this guy is greater than this guy, then the bond market collapses because nobody would like to go with the bond again. Capital gives us a lot and what's not. So this is one intuition that you can pick up. Questions? Questions?
No questions.
Let's finish up with a functional form. I'm going to use a functional form to see how we can solve this guy. So the functional form I have here is supposed to look like this. Expectation, the summation of t equals 0 to infinity.
We've got a question.
Yeah, feel free.
Can you explain the intuition behind intratemporal decision and Euler equation? Not the math, just the intuition.
The intuition behind, is it intra or inter? Which one are we looking at?
Intra.
Intra doesn't involve two-time period, right? Intra is basically making a decision as to how much you like to consume, which is a different variable, and how much you like to work, which is another variable, within the same time period. So these are two different variables that you are trying to compare and make a decision on. But what the Euler gives us in terms of the intertemporal decision making is, we have the same variable and we are trying to examine how our decision on this same variable changes across time. Is that okay? Have I answered you, or is it still not clear? Alex, if you have a mic, you can pick it up.
So Euler is intertemporal decision?
Exactly. Euler gives us the intertemporal decision-making process, right? Because it gives us the CT plus 1 and CT, or NT plus 1 and NT, or any other variable within two periods. So we have this functional form to work with, 1 minus gamma, and this is the amount of hours of work, 1 plus eta, 1 plus meta. The budget constraint is just the same, WT, NT, and we have RT, KT here. And we have 1 plus the depreciation rate here, plus RT, plus the bond, plus the profit. It should be equal to, I believe, CT plus KT plus 1 plus BT. Please let me go respond to a quick mail. I'll be back with you guys. Okay, just give me 2 minutes. So please have a look at this. This is the functional form that Lynn asked. If you have any further questions on it, please let me know. I'll be back in 2 minutes.
Sorry, Ella's just asking, what is the exponent on n at the top?
Neta. The same as the one that you have down here. It's neta. Okay? Give me 2 minutes, I'll be back soon. Yeah, further questions? Tanya?
No other questions.
Question in there. So just a quick one. I wanted to find out, do you guys have MATLAB? Is there anyone with MATLAB? Have you guys used MATLAB before? Oh, okay. I'm trying to see how we can, yeah, if you have MATLAB and you know how to use MATLAB, your TA will take you through how these guys work in terms of seeing the graphs. And yeah, let me show you what I mean by that. So when you solve for this and you put them in MATLAB, you come up with what we call the dynamic output. So you tend to see stuff that's look like this in terms of your outputs, your capital, your amount of hours of work, your consumption of and what's not. So your TA will take you through either this week or next week. If you don't have MATLAB, you can download it. Hopefully it will take you through it and see how it works. Is that okay? Is that okay, guys? And I don't intend to make it compulsory, but maybe it might be helpful if you might want to have a look at how it works and all that. So let's see. So we have this guy here. If you had to go with the first order conditions, just like what we saw, everything becomes easier. So please use what I did, try and solve this guy. And show me the intratemporal, show me the intertemporal decision making, solve for the C's, and send me the solution, and you might get one additional mark, which will compensate for the quiz. So if you want to get a bonus mark, you might want to work this guy out, the 4 equations, join them together, get what C is, get the Euler equation and all that. So try it out and let me know if you are willing to work in and send it to me. I can give you additional bonus points on the quiz for last week. Last week's quiz was average, so I can get an additional. So why not Tuesday before class? Would that work for you guys? I'll send it on Canvas. I'll create a Canvas page for it. Tuesday before. Yeah, there's gonna be a quiz this Thursday. I think most of you wanted it this Thursday, so it's gonna be this Thursday. So I'll send you another file when you guys are done and see how it works. So this will be part of your reading. So solve this guy, send me the solution, and let's see how it works. Now I'm going to introduce in the firm. The reason why I kept the firm silent is that the firm is the same as what we saw, right? The firm
we had some questions here. Ella asked, so there's only one condition here, right? I think the equation you raised.
As in terms of?
She just asked it.
Yeah, I simplified it, right? So I just changed the investment into KT, so the budget constraint is right away ready for you to use.
Okay. And then somebody else asked, what chapters will the quiz be on?
Everything up until last Thursday. Not this week, everything up until last week. Yeah. Now let's introduce in the firm. The firm has the same idea, just like what we saw in the 2-period model. The most important thing here is the shock. So this I'll try as much as possible to use this guy and answer Alex's question. So we have the output of the firm coming from KT alpha, NT, 1 minus alpha. Now I'm going to introduce in Z. So initially we had the Z to look like this, which is okay. You can also put in an exponent in front of the Z. So we have the output that the firm produces to be like this. Now the interesting idea here is that the Z has a certain level of changes. So Z is the technology, efficiency, and what's not. It moves in line with the efficiency that it inherited from the last period, plus a certain level of shock. And this is where I think I might have to spend some time. So ZT is the efficiency in front of your output, or how you produce your output. the amount of ZT today is determined by the amount of ZT that you had from the last time. Additionally, there is a certain parameter in front of your ZT which we call persistence. So when rho here is positive and higher than maybe 0.75, for instance, then we call it to be highly persistent. So whenever something happens yesterday, we still have the effect today, and the effect is positive. So that's a persistent parameter that Alex was asking the last time. Now this guy here is what we call the shock. The shock might hit you. It can be a positive shock, it can be a negative shock. When it hits you at this time period, for instance, when it's a negative shock, it is negative, so it is down. So it might bring your ZT down. And as it brings your ZT down, your YT also comes down. So that's the effect of the shock. The shock happens, it affects your ZT, and as ZT goes down, your YT also goes down. So that's how to understand a shock process. Questions? Questions?
No questions.
Good. And for the profit of the firm, it's just like what we solved the last time. Nothing interesting. So just go pick up midterm 1, look at the firm's problem, and that's how to solve the firm's problem. So that's mostly it about today. Your TA will take you through a comprehensive dynamic question where we have different level of shots. Yeah.
We've got, yeah. So rho must be less than 1.
Not necessarily, but ideally we expect it to be less than 1, but to be persistent. But it might be the case that when a shock happens, there might be a certain shock. When it happens initially, you might not feel it, but over time it will increase. It's a bit unusual. That's why I drew this graph the last time for you guys. So if this is the time and this is the shock, what is consistent with the data is when the shock hits initially, it has a high impact, then it dies off. But if you think the opposite way, that the shock happens initially, you might not feel it, but it increases over time, then the rho is greater than 1. But with this, the rho is less than 1.
And then we also had a question. So we assume that shocks are positive. So a higher shock, it makes a higher Z.
Yeah. Or I might change it to a negative shock. It depends on it depends on my mood for the day, which shock I prefer to inject in the economy. Question?
So just making sure the RBC question needs to be done before next Tuesday, right?
Yeah, the for an additional 1 point on the for the quiz. Yeah.
And then someone else asked, is all of the info today from the separate reading you emailed us, or do we also need to read anything from the textbook?
Not necessarily. The textbook doesn't have these this computational stuff, so I had to look elsewhere to get the computation for you. So that's the one I sent to you guys. So I believe if you are to attach the functional form to what we discussed today and you follow it step by step, you'll be able to pick up everything that is expected. Yeah, the textbook doesn't have the RBC in terms of the computation. Questions?
I think that's everything.
Okay then. I'll see you guys on Thursday, hopefully. Okay then. Bye-bye. Thanks, Tanya, and thanks for everyone. Okay.